after 4. So we're moving on to the signals, communications, and controls topic, actually. And we have our very first speaker already here, Tommy Cooper. Tommy, so if you guys have questions for either, me or Tommy are still here for y'all. So I guess we will be transitioning to the signals talk. So if you would like to start that off, Tommy.
Okay. So the other part was, I was trying to gear more for the hardware, but you sort of heard an underlying bit of information, that where I talked about some of the signals that we have to deal with. Sometimes we're dealing with signals that are coming from the body, electrocardiogram, electroencephalogram from the head, or muscle signals. So the types of signals we deal with, there's a whole lot of them there that are the biomedical, if you like. How do you measure someone breathing? How do you detect that? There's several methods for doing that. So we have to develop those signals and then process them. So I still live more in the analog circuitry world. So I do, some of the basic processing in the analog world. My other guys do more digital work. So those signals might get processed in the analog world or digital world. But those basic principles all apply. In other words, the filter technologies that you learn, they can be implemented in the analog world, in the circuitry, or over in the digital world. And right now, so we're doing everything from signals. So one of the interesting things that's sitting here above me is I have a bag of saline fluid that is going to be delivered to a patient, and it's with the pressure infuser. So how do you measure the volume delivered to the patient if you can't put a flow probe on it? How do you measure the volume delivered to the patient? How do you tell the size of the bag? How do you tell whether the bag is full or empty? Well, there are several techniques that we've implemented. You talk about signals. So one of the things we get is, you guys remember your pressure, your Boyle's law, your gas laws from chemistry almost in physics. PV equal nRT. So we've developed technology that will actually monitor the air pressure pumped into the air pressure pumped into this cuff that we pressure up to 300 millimeters mercury to drive fluid into that patient. And by knowing, so then we pressurize it, say, to 300, and then let it drop down to 250. So we can use that signal to estimate the amount of volume delivered using the gas laws. If you follow, these are all signals. Another way we measure it is we measure the impedance of the fluid. That's a conductive fluid. So we can put on electrodes and measure that impedance with like an AC ohmmeter, where you have a 4-wire ohmmeter, you put current in and then you measure the voltage coming back. That's how that works. So signals are our life in a way, because that's you need that information, whether it's right off the body or whether it's in the equipment. We have other signals that we're measuring that have to do with lasers, and the ability to find these signals and measure them. For one of the lasers puts out a remarkably high intensity pulse into the body, and I don't know whether any of you have ever heard of something called optoacoustic technology. So optoacoustic technology involves use of a pulsed laser light. So it's pulsed at a distinct and singular. In other words, it's a very tightly controlled wavelength. And that wavelength, as it's pulsed and it goes into the body, certain wavelengths are absorbed more readily by some of the parameters. So one of the signals we're looking for is it's absorbed by hemoglobin in the blood. And whenever it's absorbed by that, it goes to a thermal expansion, and the thermal expansion presents itself as an acoustic wave. So optics to excite it, acoustics is what you're sensing. This is a very small acoustic wave. So we're able to sense that with an acoustic sensor. And then we had to do it about 1,000 times and average the signal to be able to even see the element that we're looking for. And it's got a depth. So all of these things involve signals and how you then are able to extract those and get measurement. So when you ask that sort of question and look at it, this is part of what is interesting to me, and what's been the kind of fun part of my career is being able to work on those kind of things, but also controls. So I said early in my career, I worked on artificial hearts and those types of things. So at one point, we were designing the controls for an artificial heart. Those back then, those artificial hearts had they had one-way valves going in and out of them, and they had a polyurethane bladder inside them. So think of a spherical device that has a input port and an output port kind of coming up the bottom half of the sphere. The top half, it's air driven, so they would suck on the bladder and pull blood into it, and then when it got full, they would turn the pressure around and drive air into it and drive it out. It would come in through one valve and go out the other one, sort of like a heart. This was a pole pump. We developed a technique that measured electrical capacitance of that bladder as it approached the inside of that shell, and we could tell how much volume was inside the pump. And then we would know when to trigger it to go empty and full, because it had to stay in motion all the time. So there's always these aspects of it, whether it's electronics or controls or signals. These are all things you're dealing with and processing. So anyway, maybe leave it open for some questions, or no?
Yeah, most certainly. If there's questions, I mean, it's what we're here for, right?
I can talk about some other things in that regard.
We can do either. I guess we might as well just take a call for questions just in case somebody's got something stirring, and if not, we can keep going.
Okay, well, y'all just put them on the chat thing, or kind of raise your hand, or however that works, and we'll kind of stop and talk to you about them. So one of the things I had was basic control theory, which was how to design a control system and how to optimize the response of it, like the step response, if you like. So one of my early projects was a system that pumped blood around the heart. It was a bypass pump. So one of the things you do whenever, one of the ways the heart fails is the heart has two chambers. The right chamber, the right side of your heart, is pumping blood up through the lungs. The left side receives that and pumps it to the rest of the body, which then circulates back to the right half. What fails many times in a heart is the left side, the part that's doing the most work and pumping the blood to the body. So they'll do a left ventricular bypass pump. So we did this with a roller pump, and we put a catheter up in the above that chamber in the right and the left atrium and pumped it to the aorta. So one of the things they did is one of the things that happens whenever the left heart fails is the pressure, the drive pressure forcing blood into that ventricle is the left atrial pressure, and that pressure starts rising up. And whenever it gets up high enough, it actually, the lungs start filling with fluid. So you want to get that left atrial pressure lowered back to its nominal value, which is maybe 5 to 10 millimeters of mercury. So I did a system that would do a servo control on the left atrial pressure. We would dial in. I want the left atrial pressure to be 10. It's 30 right now. And so it was a classic analog servo control system with negative feedback. Now, the thing I didn't know was how to compensate it. So I put in a whole bunch of lead lag networks that would compensate that. Now, most of you all are going to be using the classic, what is it, proportional, differential, and integrated, a PID technique to do your controls. I've used those too. But that particular one, what I did was I had all these, a little PC board switch that I could switch in resistors and capacitors. I had them clamp the aorta so that our pump would take over full left ventricular flow and then release it. And I could do a step function and see what the overshoot and ringing was. And I switched in the lead lag network to compensate and optimize the response. So control theory is something that has applications across so many things. Later in my career, which is, more in the last 5 to 10 years, designed a dialysis system for It's used not like the dialysis that you go 3 times a week and get your blood cleansed, if you like. That's for chronic dialysis. Somebody's in kidney failure and they need to go for dialysis. This machine is used in the intensive care units, and it's mainly used on people who are in congestive heart failure. So this machine will run on that patient, and it pulls blood out of the body, and it performs the kidney functions. It removes fluid, it balances acid base, it balances electrolytes, and so we designed the system that would do that. It runs 24 hours a day, pulls blood out of the body, and eventually a patient will come in and congestive heart failure. They have fluid overload and they're in cardiac instability. So you have to do this very slowly. Well, here was the key part with the control system. It wasn't only controlling the individual motors on the pumps. We had to measure the volume delivered and taken out of that patient very precisely, like 0.05%. But we had to, you couldn't get the pumps to have very high accuracy. So in order to control the pumps, I had to design a control system that was basically a servo control that would modify the pumps to balance that fluid. So this control theory, now I used a custom, like I designed my own control algorithm, but it was basically a PID. It was used proportional and integrating type control for that. So this technology, as you learn it, can apply to just such a wide range of different applications. Okay. So one of them is, do you think, can you go over what controls is? Did some of that cover it? This was, okay. All right, good. So I wanted to know the difference between signals and computer embedded systems as concentrations. Okay. So, so signal theory and signals in general, part of that is how you process signals. So what type of sampling, and when you digitize signals, you have to know quite a bit about the signal and what the signal of interest is. So as you develop your circuitry and your preconditioning before you bring it in and digitize a signal, you have to know a lot about that signal, and you have to precondition it so that what you're presenting to the digitizing system is something that has a limited bandwidth, among other things, because you can get something called aliasing errors, among other things, that if you are sampling and the signals coming in are too high a frequency, then you're not sampling them fast enough. So all of these types of things are part of signals and the preconditioning of them. So another thing you have to learn is there's such a wide array of filtering techniques that you need to learn, and you need to know just a remarkable amount, and you get most of it in your undergraduate courses on signal theory and signal processing, about Fourier analysis, and this helps you understand how to work with signals and how to modulate them, how to demodulate them, how to acquire them, all of that. It tells you, it gives you the background so that you understand it, and you precondition and sample those signals properly to get them into your embedded system so you can work with them. I hope that helps. I actually didn't get to take the actual signal processing course, but all my people have, and so they've actually supplemented my knowledge in it in terms of making sure that we don't make any miscalculations in our processing of signals. And trust me, it's easy to do. You can screw that up. So going over some of the classes you might take. Well, I'm not as familiar with the present curriculum. So when I was going through, there was they had a couple of courses in control theory, and I took those. And there was also a course in signals, and it's all of that information about learning how to analyze signals and how to break them down and how to filter them. I also took a course in digital filtering, and that course was remarkably helpful. That was like a senior level course. Some of those basic courses in signal conditioning, I wish I knew all the curriculum so I could point to the actual coursework. Maybe somebody else knows. Okay.
Well, do we have any more questions for Tommy? I know he's been really helpful to me. I know that's for sure. I always love learning something new.
Okay. Well, I hope that there's some of you that like the embedded systems and like the signal processing and like controls. Your ability to use the techniques you'll learn. You get to work on the most interesting projects. It was always fascinating to me to be able to do the control algorithms and to watch what happens and to get all that working properly, so that if you needed to control a pump speed, control even some motors that run carts and things like that, all of those things come into play. And it kind of married in with my hardware. So the hardware, the part of it, the electronics part of it, and the controls and signals, it's all kind of tied together for me, along with the embedded processors and so forth. So.
All righty then. Well, if nobody has any questions, thank you very much, Tommy, for coming out. Thank you for presenting on electronics and for presenting on signals. Oh, here we go. We have one more question. It's all good, Tom. If y'all have questions, ask away. I'm not in a rush unless Tommy.
Whether it's your senior design project or whether it's trying to get an internship in your area of interest, getting that experience early and getting exposed. I was very fortunate, and I got to work with the hardware area. I was looking for it, and I finally got it, such that I got to work in those hardware areas and work on systems and hardware. And early in my career, some of it is how you look for your jobs and what you're doing. A lot of these got presented to me because of the areas I was in. When I was working at Baylor so long ago, we were working on a number of systems in our lab, and we had one of the surgical students came through on a rotation to our lab. He was going for becoming a medical doctor, but he had a MSEE from Rice. And he came up with this idea for controlling a clinical pump that we had that was used on patients that they had the difficulty getting them off the heart-lung machine and put them on something called an intra-aortic balloon pump. I was kind of responsible for that clinical system in our lab. He had a way he wanted to implement a control in it that he thought would make it work better. So he wanted to design a microprocessor-based system. This was in 1976. So think about that a minute. All this stuff you have now, we have all these microcontrollers and all these development systems, and it's so easy to do this. You just program them up. You've got evaluation boards. We didn't even have evaluation boards. We had to go build our own evaluation board and our own programmers. So the way we programmed it was we had thumb wheel switches that were hex switches. We would dial in the address, dial in the data, and hit store. So, but it's back to that question of how do you get that experience? You're going to have to seek it out in terms of internships and the courses you take and the labs you take, so that you can get that. If you like doing embedded processors, and I really love working in systems that have embedded processors. I've got one being designed right now that we do all these things with. So those are, to me, the most fun ones are those battery operated embedded systems that have a lot of signals and processing. So the job titles, you know, those job titles are going to still be electrical engineer, project engineer, and so forth. It's kind of what the job description is, what does it entail, and what functions they're looking for. That's how you're going to be able to tell.
Man, they're all fired up with chat questions, that's for sure.
Let's see what we got here. Miss the electronic part of it. Can you talk a bit about favorite parts? So, as far as the electronics part of it, I've kind of covered a little bit of it there. So I told you I did a microprocessor based systems. So back then you had these 40-pin, they were huge chips. And you had a CPU chip and you had a peripheral input output chip. You had a separate chip for everything. And we wire wrapped it all together. We didn't even get a PC board laid out. So that's the level of things I worked with a long time ago. And because I did that work with that microprocessor, my first job when I left Baylor College of Medicine, I was deemed the microprocessor expert. And so I designed a defibrillator monitor system using a microprocessor. So it's getting your feet wet is the most important.
Did you cover the question about potential job title?
Well, again, they aren't going to say, well, they might say hardware engineer, but many times it's going to say electrical engineer, project engineer, that type of thing. You're going to get that electronics at a level that is where it's not going to be project manager. It's not going to be, you know, it's going to be more down at that electronics level where they call it electrical engineer or project engineer is what I would think that the job title is. It's looking at what they're looking for that engineer to do. You know, what's the description of the type of work? And it'll say embedded systems. It'll say hardware. It'll say power supplies. It'll say all those different things. It'll mention that in the job description. But the job title is probably still going to be electrical engineer, systems engineer, or more likely maybe hardware engineer.
All right, cool. Yeah, I asked because I dropped out for a second and I wanted to make sure. So, all right, do we have any more questions for our great presenter, Tommy? I'll give you guys another minute, I guess. All right, well, I'm not hearing any, so.
All right.
So.
Well.
Thank you very much for coming.
I enjoyed talking with you guys.
Yes, sir. We really appreciate it. And if anybody wants to reach out, here's a question. If anybody wants to reach out to you, how do they do it?
So here's my email. It's tgcooper@sbcglobal.net.
All right. I believe I typed that up correctly.
Yeah, I'll say it again. tgcooper@sbcglobal. You got a J in there, is all you got, but sbcglobal.net. Close.
There we go. That should be right.
That's it.
All right, cool. Well, thank you very much for coming out. If you want to stick around, feel free. But if you have work, we understand that too.
Yeah, I've got to run off. I got stuff.
All right. Well, thank you very much for coming out. We really appreciate it.
You bet. You guys take care.
You too, Tommy. All right. So our next presenter is a wonderful person who I went to school with, named Leslie Nix.
Oh, that's an excellent intro, Colin. I need that kind of intro at the beginning of every meeting I'm in.
All right, well, here,
Anyway.
I'll do another one. Introducing Leslie Nix. Yeah.
Excellent, wonderful. So I'll be the person that can tell you a little bit more about the classes that you'll be taking. Because I graduated last December. I'm currently the lead platform security engineer at Shoebox. So if you're asking about job titles, that's what mine is. It doesn't mean anything to anyone who isn't me. But basically, I work in cybersecurity, mostly doing putting out small fires. Like if you keep up with tech news, which is something I have to do, there's a unfortunate vulnerability in a TCP IP stack and a lot of different I don't want to say software, that's not the right word, firmware, I suppose. So I have to wait for patches to come out, implement those when they happen, and until then, just quietly panic, hoping no one will take our data, because we're an enterprise software company, so we handle a lot of very sensitive legal and financial information for our clients. And kind of like the SolarWinds attack affected a lot of people, it'd be the same thing if my company got hacked, is that we're small, there's like 50 of us, like, not a big deal. But our clients, some of them are major companies that were those kinds of attacks to spread throughout our network or throughout our software platform. That would be very unfortunate. So let's see, classes you take in Signals. What did I take? So you take, well, you start out taking Signals, right? So that's the first class, everyone's got to take that. I love that class.
I can pull up the degree plan if you'd like, Leslie.
That'd be nice, actually, yeah. But yeah, I do remember,
I had it earlier, so.
Yeah, I do remember that, yeah, I love Signals, so I was like, ooh, I love Signals, I'm gonna do this. I might have been the only person to have ever loved that class. So just so you know, it's not required for that. Okay, so yeah, digital signal processing. Yeah, I think Tommy talked a bit about that, but I would agree that that is an incredibly important class. Especially because most people don't work in analog signal processing as much anymore. I mean, there's certainly those jobs are out there, and certainly for legacy systems or in situations where you just don't have the infrastructure to do a lot of digital signal processing, you'll need some analog signal processing skills, and that's what you'll learn in signals and systems. But when you convert to digital systems, which of course are very prevalent, especially in embedded systems, because microprocessors can be very, very cheap. They can also get very, very expensive, but they're generally very cheap, very powerful, and you can do quite a bit with them. But when you move into the digital realm, you end up having a lot of issues with, like Tommy said, the bandwidth of the signal and aliasing, and you have to understand quite a bit about the signal you're looking into. You also have to do a lot of things like removing noise from a system, especially if it's in motion. My senior design project was designing a autonomous quadcopter, which was a lot of signal processing, a lot of removing noise from cheap garbage sensors that we bought off like Amazon. A lot of fun, but a lot of work, and there's definitely quite a bit of math involved in it. Actually, will say that I think signals, communications, and controls, it is very close to embedded, and I know that's a very kind of popular choice people are making. When I did this last semester, it was kind of the same thing. How do I choose between the two? I don't know. I'm sorry. I picked signals, but I will say that these classes do tend to be a little bit more mathy, I suppose, than embedded. That being said, I didn't take embedded classes, but I feel like you end up doing a little bit more like actual calculations, learning the theory in signals concentration. Let's see. Advanced telecom, which is now apparently not just telecom, it's now advanced telecom, which is what I took, which sounds terrifying because you're like, advanced telecom, I don't know any telecom. But that was actually a very interesting class. I didn't want to take it because I was like, I don't want to work for like AT&T or anyone. But it's really interesting. So when I was talking about like that TCP/IP vulnerability that I'm dealing with right now, you learn a lot of those kind of communication protocols in that class. You'll certainly learn more about that, I'm sure, in a computer networking class. You do have quite a bit of programming. So Intro to DSP, you have a very large programming project. I think Chef Still's the one who teaches that class. He's been like trying so hard to get people, or to get the what is it, the college, to turn that into a 4-hour course, but then the hours end up getting really ugly. But of course, digital signal processing, you're processing digital signals, you're doing it digitally, you're going to be writing all that code. I think it was in MATLAB. Telecom was more of a hardware-based lab because we had kind of that hybrid semester. You could also do digital telecom kind of stuff. I believe that was also done in MATLAB. I'm not sure. I did the on-campus version. And then the other class you take, control systems. Did we do coding? I don't think we did any coding in that class, but I also took it in kind of a weird semester where I didn't have a lab because no one was teaching the lab. So we just like all got credit for the lab, but no one actually did anything, which ended up being really kind of unfortunate because I wanted to go into control system design and go into more like robotics. So I was a little concerned. I was like, wow, I have no practical hands-on experience. Luckily, I did a robotics kind of internship that kind of bridged that gap.
Yep,
Let's see, what other kinds? Yeah, it was fun. I really enjoy control systems, although it sounds like I've kind of gone to the dark side into like computer science. I really haven't. The reason that I'm the security engineer and not a security analyst, which is what all the other members of my team are called, is because I do have that engineering background. So I don't really spend a lot of time like staring at the computer, like watching attacks trickle in, which happens so frequently. It's actually kind of funny because you just see them and it's like they're just like pinging the window, like, I don't know, driving through a small hailstorm. But like your normal antivirus software will catch those, no problem. I don't even have to think about them. It's just people, I don't know, are lazy and bored. So they just attack everything they can find. And they're using, you know, exploits that are like 10 years old. And it's like, that's not going to work on my system because I'm not really dumb like you are apparently. But the analysts, they deal with that. And they're the ones who have to watch, you know, our network traffic looking for anything strange like that. My job is more designing the defense policies. So making sure that no one gets in. So while the analysts kind of do a little more of the offensive work, they're like, you know, looking for people breaking in and try to, you know, mess them up. My job is more designing the policies and protocols in place. And so it doesn't sound like I do a lot of engineering, but a lot of the work I'm doing, especially because it ends up being more research oriented. I'm going to kind of tie this job in with my master's, which I'll be starting at CU Boulder, is kind of using digital control systems and some machine learning algorithms to kind of envelop our software in this kind of blanket that can recognize these kinds of malicious patterns that attackers use to gain entry into these systems, as well as looking a little more closely into hardware security. So if you really want to like go into signals and embedded, hardware cybersecurity will be right there, because with that, you're actually kind of designing things more in silicon, which I think would be kind of the main difference between my interest with embedded computing systems versus what an embedded person would do. I imagine they would design the silicon, whereas I'm just like, hey, I'm gonna just use this real quick, and maybe I have to build my own little breakout board here and there, but mostly I buy a chip that already exists. Let's see, other classes I took. So I took circuits and systems. That's just a great class, I think, for anyone to take. That's where you get your three-phase power. If you want to do anything even remotely power-ish, you're going to need that class. I enjoyed it, even though I am not a power person. I don't like big electronics. I like little electronics. But it's a great class because you at least get kind of that fundamental understanding. And because this is Houston, even if you go into like electronics or signal processing, it's still very good to kind of understand the basics of that. I also thought it was the easiest elective in the entire department. That's me, and that's my opinion.
That class was easy.
Yeah, okay, yeah, I'm not the only one. Yeah,
I really enjoyed that class just because three-phase was, so that class was 3364, which is circuits and systems.
Yeah, circuits and systems. As far as I'm concerned,
so
it's
maybe that's kind of unfair, but yeah. I honestly really enjoyed it.
I enjoyed it. It's a Hebert class, so if you've taken a class with him, it's just like any other of his classes. But yeah, the material is very straightforward.
It's the best.
You just have to kind of sit with it.
Hebert, if you take him, personally.
I don't know. I took C programming with him over the summer, and that was fine. But I already knew programming, so maybe that's a bad thing for me to say. I already knew what I was doing in that class. I just kind of sat there and was like, okay, I will do this. And then we like stopped that course right before you get into like building queues or stacks. And I was like, or linked lists. And I was like, that's like the part that matters. Anyway, I didn't take embedded, but I did take microwave engineering. That was a really interesting class. I took it because a friend of mine told me to take it, and that class was objectively hard. It was an objectively difficult class. It's if you don't like EM, you will not like that class. I really liked EM. I was magically good at it for no reason whatsoever. I was not the same way in microwave engineering, but you do also, it actually ties in really well with communication systems. So people like to joke like, oh, but I have a microwave in my kitchen. Like, why are you building another one? Like, no. They're using, fancy radar systems. It's a little bit different than that. So if you do want to go into kind of that aspect, you can take that class. I only recommend it if you really like EM because it is EM more. It's more EM. So if you struggle with that class, you will struggle with microwave engineering. I'd recommend not taking that class if you don't have to or don't love that. State-space control systems is a lot like automatic control systems. You end up working more with like a linear algebra version of it. So everything's now, instead of being a number, it's now matrix. So there's some matrix math involved. It's not that big a deal. Don't panic. But that's great. It's absolutely necessary if you want to design slightly more complex control systems, because automatic controls, you only learn about the PID controller, and it will only work for a single input, single output. So like, I'm going to read temperature and like turn on this thermostat, which is a terrible type of control system, but there it is. But if you want to do something more complicated, like, hey, I want to read this input and that input and that input, and then depending on some control scheme I've set up, do this and that, and also that thing over there. And to be able to do those MIMO systems, the multi-input, multi-output, you need something more like state space, which is, I thought it was a really fun class. I hear in the normal times that the lab project for that class is developing a control system for a quadcopter. So maybe do that instead of doing my silly senior design thing, or both, right? You'll be better at it. Let's see, I wanted to take advanced digital design, but that class is really hard to take if you are not a computer engineering student or an embedded systems specialization. So if you really want to take that class, and that's like the whole reason you went to college, then do not pick a signals concentration, because there's a limit to the number of people who can take that class based on the number of boards that are available for students to work with. And you're going to have a really hard time getting into that class if you are not either a computer engineering student because I believe they have to take it, or computer and embedded because they just don't have a lot of options. Internet networking I didn't take. I took cybersecurity, great class, loved it. It's more cryptography than anything else. So you're learning more about all the different encryption algorithms and how they work, how to break them, how to make them stronger. Intro to machine learning, wonderful class. There's quite a bit of coding involved. There's an amount of math, like in the lecture slides and stuff. There's an amount of math to know about, designing optimal algorithms, things like that. Having your good search parameters, but it's not a lot. It's very interesting. Of course, machine learning is kind of one of those like big things right now. So highly recommend that class. Super fun, super interesting. I use it. I also took robotics, which is very fun. More math, a lot of math actually in this concentration, especially the way I went about it, because I'm also a math minor. I like math. So I like learning these kind of theories. But I think overall, my favorite thing about this concentration is that it is so broadly applicable. You can do a signals concentration and then maybe you have to do a couple other things, but then you can like go into hardware design or go into power. You can go into a good old fashioned electrical design where you're just kind of doing like, power and lighting and such for a building, which is probably the most boring thing you can do. But it's a thing you can do with possibly any concentration. You can go into aerospace, you can go into what I do, which is kind of computer science, and then just be like, hey, you're all computer scientists and I'm not, and now I'm in charge of you. Sorry. So I think that is every class I took. We have any specific questions or things? I feel like I lost the chat somewhere. We have coding and programming. Yes, we have coding and programming. I can't compare it to embedded because I didn't take that class. And then, yeah, circuits and systems being an awesome, relatively simple class. That's generally applicable. It'll probably be the one class I took that wasn't class I wish I took. I wanted to take advanced digital design. And there's very specific reason that everyone wants to take that class. And it's because of the technology you use in that class. You're not going to get it in any other class. It's very different from other classes in that regard, because you're not just working with, some random microprocessor. You're working with the FPGA. And when I wanted to go into more specifically to control systems, that's a kind of technology that they would like you to know how to do. Same with PLC programming and ladder logic. Which is also not available in a class unless Trumbetta is still doing that like mini thing.
I'd have
Colin
to
might have more
ask you,
information on
there
that.
is a specific, if y'all are curious on what she's talking about, there's a specific lab dedicated to PLCs, although it's really more of a fluid class where you get to play with PLCs and learn about them as you go. I took that. It was awesome. But that I believe is a specifically, I believe they are doing it. But you specifically have to talk to Trumbetta to get enrolled in that class. Although you will learn ladder logic, PLCs, and get to play with them, and it's a lot of fun. It's its own. It's like, if you understand when I say binary logic, it's literally binary logic coding. It's very fun.
Yeah, so okay.
That's a good question.
I mean, yeah, so
I look back now, I'll just put my input in, then onto you. And when I look back on signals and systems, I didn't like that class very much. Ironic, because I look back now and it's like so integral to everything I have all my other classes, and it's like, why did I find this so hard? And it's kind of weird.
Take it with?
Roysum.
Were you in my class? You might have been in my class, and I just totally forgot.
Yeah. I was in your class. That I think on the row over from me. Something like that.
Oh, yeah, that's right. I think you sat like there.
You sat in like the second row, I don't know the left or right side. I think the right side.
Well, I sat like all the way in the back and then I moved to the front to sit with Fernanda.
Yep, I
But
remember.
yeah,
That's one thing.
none of that's important, guys.
Is
Yeah, so
Royce
I also took him.
good?
Yeah, I took him with Royston. I think
I thought it
people
was
who
good.
take the class with Royston like the class a little bit better.
I heard Trombetta was good too. Although as I remember, Trombetta was having to learn it the same semester we were taking it with Royce. So
That's a good point. Yeah, that's a good point. Yeah, when we took it, we just had Royston had been teaching it forever, so he was like very organized.
Yep. Royston was good to take it with. I will say, when I took it personally, it was hard, mainly just because it was a lot of work and I had a really bad. It was probably my worst semester just because of all the classes I was taking specifically. But it's so integral to everything. Like when I look back, just because of how exposed I've been to everything by now, I look back and it's honestly not too bad. Leslie can probably second that to some degree.
Oh, I could absolutely do that because yeah, that's like my whole argument for going into signals is that at the end of the day, like everyone's gonna have to do a little bit of signal processing because we're engineers and like we're dealing with signals. And I mean, you don't have to be like, I love this. This is all I want to do. Like all I want to do is like look at like wavy things that are really noisy and then take the noise out. I mean, I think that's not even a job you can do. Most things are a little more integrated now. There's a little more, I have to know a little bit about embedded, know a little bit about everything. But I guess to answer your question, if you're not like doing a good job in signals and systems, I think it's like any other class. You have to kind of figure out why. If it's like you're not like vibing with the material, even though you're putting in a lot of effort, like a disproportionate amount of effort compared to other engineering classes, then I don't know. I feel like you're definitely gonna have some trouble. Yeah.
It's like one of those things that just takes time to click. You just have to study it long enough, and then eventually it'll kind of click, I guess. It's kind of like engineering in general.
Yeah, I think if I remember correctly, it's one of like the first classes you take that's like engineering, right? So you're taking like circuits, which is hard in a very different kind of way. But yeah, the signals classes. The material is tricky. I think it depends. And then, yeah, of course, you're taking classes in a weird situation that is probably going to make everything harder or weirder. So it's kind of hard to transfer that experience. But I will say, if you're having a hard time with the material and you're trying really hard, and it's like you're just not vibing with it, you're going to have a hard time in digital signal processing. You're going to have a hard time in telecom. You'll be okay in controls.
Yeah, it's
that's not too much signals.
It's a little different.
Yeah, but you're gonna have a really hard time in telecom. You're gonna have a really hard time in DSP.
And here's
because
one
you
thing
need
I
to
learned.
know that information.
There's one thing I learned, which if I believe if y'all went to the general session, the general advice session that Trombetta and Amanda gave, y'all probably would have heard this. I believe in the fall, as far as the ECE department is pushing, they're going pretty much back online as far as undergrads are concerned, or back in person as far as the ECE department is concerned for undergrads. Now I said that's what Trombetta, I believe, told me. So take it with a grain of salt.
It's gonna be what it's gonna be, right? It's fine. Anyway, telecoms. So a lot of that class is about dealing with signals also, an amount of signals and signal processing, but these signals are not coming through a wire and they're not digital. They're through the air, as telecoms are wont to be. So it's kind of it's a very survey course, because telecom is telecommunications. It's a very large field because you have your cell phone, which is 4G, 5G, however many Gs, 27 Gs, I don't know anymore. You have your Wi-Fi, you have, geostationary GPS satellites, you have all sorts of different, networks and access points. And so you kind of get a a broad survey of all of that, as well as some of the problems involved with, different bandwidths of signals, and kind of different kinds of noise you can experience due to either, your receiver's moving, but the transponder is stationary, it's the other way around. You have to like go through a concrete wall, which kind of just kills your signal ultimately. But you have to learn about kind of those different kinds of signal attenuation, how to deal with the noise. There's some math. There's always some math. There's a couple math problems on those tests. All I remember.
So
Kind of blocked out that class. It was very early in the morning.
Yeah. So I'm seeing a question that says, what was the binary coding class? So binary coding, that's just my way of saying it, but it's called ladder logic. It's also known as PLCs or programmable logic controllers. It's not a class, it is a lab, but it's like one of those special labs where you have to specifically request to be in it, and the only person that really controls that is Trumbetta. So you literally just have to go talk to Trumbetta and say, yo, is this class happening this semester? And it very likely is. And then just say, I want in it. And to some degree, you kind of have to have a reason. I think for me, I had to have, I guess that's not really a great way of saying it, but I took it. When I took it a couple semesters ago, before it was a semester before everything went online, we had 6 people in there. It was great. It was awesome. But that's pretty much that. So I say binary coding, but it literally just means that you have something either something is on or it's off. Now it sounds very simple. It actually gets very complicated, but it's unlike any coding out there because it's visual coding. It is not really written coding. You can integrate that into it, but it is visual coding, and it's made for really interesting way to control different things like motors and lights and processes. It's its own thing. It's what a lot of control systems are built with as far as plants, factories, etc. are. So
yeah, it's incredibly common in control systems engineering outside of robotics, which is its own whole different ball game of stuff. But yeah, if you want to get a job that's like your job title is like control system engineer or automation engineer, which usually means that you're automating some sort of process, either chemical or some sort of factory manufacturing process. Yeah, that's going to be your bread and butter. So if you have the opportunity and that's what you want to do, you really want to do that, try to learn that either through that little fake lab course or get an internship in it, of course, which is equally as good, if not better, because you might get a job out of it if you do a good job at your internship. But yeah, very interesting class. I didn't get to take it because it was at the same time of something else I was taking and I couldn't. I was very sad. And then a pandemic struck.
all right, with that, we're nearing 5 o'clock. So are there any more questions for our great presenter, Leslie?
Oh, absolutely. Let's see, what is my, this is a school thing, so use my school email, which is fake because I'm not a student anymore, but feel free to email me at that address. That's where I'm most likely to find school related things. If you send that, like those questions to my work email, I'm probably gonna think you're like attacking my company. Like you're asking oddly specific questions. Yeah, specific questions about my hardware. I don't like that.
Here's the question. Do you own a Linux computer?
I do actually. I have a netbook that I bought in 2010, and it's a netbook from 2010, which you'll note is not actually a thing that anyone owns anymore, except me, who does, and it runs Puppy Linux because that's like the only thing it can run.
Nice, very nice.
Yeah, I use it to. I have a home server that I built, and I guess the server is also Linux, but it's not the same kind of thing as a Linux computer. And I use that as kind of like the control interface for streaming my music, my movies, whatever throughout my house.
Well, that's the way to do it. Well, I'll give you guys another minute for questions. So as we're wrapping up, thank you guys for coming. Thank you, Leslie, for coming, and we really appreciate it. We'll be here tomorrow for nanotechnology systems. We got 2 engineers, one working, one retired, and then we will have the computer and embedded concentration as well, which will have, I believe, a working engineer and Dr. Chin's coming back. So tune in for that. Any more questions before we close out? Any for Leslie, myself? You got one. How's Colorado?
It's cold. Although I will say we had a really big blizzard a couple weeks after y'all had your big blizzard, and I didn't lose power.
The mini ice age.
But no, it's good. We actually have some really interesting weather right now where it's been raining for a couple of days. And by raining, I mean during the day it rains, but then at night it's snow. And then everything's covered in ice. And then when you wake up, it's snowing, but everything's melting. So we're in that like weird slushy spring stage. But
Yeah.
I don't know. I like it. I like the cold. The
I
cold
do
never
too.
bothered me anyway.
Colorado, A+. Well, it looks like I think the only thing that me said was you have free snow cones. So, all right. Well, if there's no more questions, thank you, Leslie, for coming out. Thank you guys for coming and participating. And I look forward to hopefully seeing you guys tomorrow. With that, you guys have a great day.